Alright everybody, this is going to be my quick video on going through this homework, the Math of Chemistry workbook. I hope I have enough time before class here. I have only about 30 minutes. So here we go. So I'm going to go ahead and zoom in a little bit here. Go up to 100%. So at the top here, we have some background information. We have a couple of paragraphs about accuracy and precision. So I'll just go through and start by reading those out loud to you. Accuracy and precision are two scientific terms that are often confused because of how we tend to use them in real life. Accuracy is how close a measurement comes to the true or accepted value, and precision is being able to reproduce a set of measurements. Accuracy and precision matter in science because scientists want to make sure they achieve the accepted results repeatedly. Many times, the tool that a scientist uses limits the degree of accuracy and precision of the measurement. For example, doctors don't use a tree saw to perform LASIK eye surgery. Instead, they use finely calibrated lasers. The greater the calibration of a tool, the more likely a scientist is to get a repeated measurement, and therefore the higher the degree of precision. In the same way, a graduated cylinder has more markings than a beaker, so a scientist is more likely to pour the true value of the liquid. The graduated cylinder is said to be accurate. So based on those two paragraphs, what you would do here is, in your own words, and that means not copy-pasting, that means not copying word from word, that means you don't type exactly what it says here. In your own words, give a definition of accuracy and a definition of precision. Below that, we have a target here. So if we were imagining throwing darts as an activity that we're doing instead of measuring. If we imagine we're throwing darts and the true or accurate value is in the bullseye, we want to see what would the pattern of darts look like if we had high precision, high accuracy, then one for high precision, low accuracy, and one for low precision, low accuracy. So I'm just going to grab a little star up here, and what I would do is I would go ahead and draw that. I'm going to hit Control-C, Control-V, and that allows me to paste. And I'm going to put the stars wherever I think they belong, blah, blah, blah. This is not the actual pattern. This is just me showing you how to place stars on the PowerPoint so that you get, so you can put in the pattern. All right. Now below that, let's see. A precise measuring tool can measure values in very small increments. Okay. So, reading that, a precise measuring tool can measure values in very small increments. Order the following time measurement tools. So when it says order, it means sort them. You can see this arrow on the right hand side says most precise at the top, least precise at the bottom. So, just to be clear also, this was not well designed. Atomic clock here. Oops, let me get rid of that fill. No fill. Atomic clock is one word. So there are really only 5 things here. There's wall clock, stopwatch, sundial, atomic clock, and calendar. So you are supposed to sort those in terms of most precise to the least precise. So if you thought that, for example, and this is not the case, but if you thought that the sundial was the most precise, you would do sundial, and then you do something else below it, like stopwatch, and then you do something else, all right? But it is up to you to figure out what is the most precise, meaning measures values in very small increments, and what is the least precise. Down here, why do eye surgeons use robotic lasers when performing surgery? And over here, if you turn your head to the side, you can see it says, be sure to use the terms accuracy and precision. So, I would like you to use the terms accuracy and precision when you answer this question. And right up here, remember it talked about doctors using lasers to perform eye surgery. So go ahead and read that and read what accuracy and precision mean. Think about what eye surgery involves. So like, what part of the body are you working on? Are you working on a large part of the body or a small part of the body? What happens if you mess up a little? Think about those kinds of things and then answer in full sentences Why do eye surgeons use robotic lasers when performing surgery? And just so you know, when I say full sentences, that does not mean you say, because this. Because something is not a full sentence. A full sentence would be, eye surgeons use robotic lasers when performing surgery because something something. So use a full sentence, please. All right, here, all I was looking for was for you to tell me, is each of these data sets high precision or low precision? So you check one of these two boxes at the top. And then is it high accuracy or low accuracy? And so you check the other box. Now you don't actually have to check the box, but the point is it can be either high precision or low precision and either high accuracy or low accuracy for the whole data set, not just for one individual data point. Right here you've got your true value, so that will tell you how accurate it is, and then you compare these data points to each other to see how precise they are. And below, I want you to explain why you chose what you chose, high accuracy or low accuracy, and high precision or low precision, and why you chose that. All right? Same deal for this data set. All right, next page. Let's go ahead and read the text again. When taking scientific measurements, the goal is to measure accurately and with precision. In certain situations in the lab, you may be measuring a quantity that has an accepted value. The difference between your measured result and the accepted value is the error in the result. Remember, error means a mistake. It means how far off you are from the correct result. You want a small error, not a large error. Scientists don't just measure once, but instead take a number of separate measurements. This eliminates any outlier results or results that don't fit the expected outcomes and allow for an average value to be taken. Okay, so that means that if you're measuring a bunch of different times and you're getting a little bit of variation in those measurements, you want to then take the average of those to smooth out that variation, and that average becomes your measured value. All right? So your measured value is, you don't just pick one of the measurements that you take all of them, and then you take their average, and that average becomes your measured value. We've got some definitions of accuracy, precision, error, and percent error to help remind yourself. Okay, over here. Now, we've got a word problem. A gold coin has an accepted diameter of 28.054 millimeters. Two students are asked to measure the diameter of 4 gold coins. Student A uses a simple plastic ruler. Student B uses a precision measuring tool called a micrometer. So student A has a plastic ruler and measured 4 different coins and got these 4 measurements. So then we want to calculate the average value for each set of measurements. I will go ahead and tell you, because we did this in class. The average, or the mean, equals the sum of the values divided by the number of values. So, for example, here we have 27.9 millimeters plus 28.0 millimeters plus 27.8 millimeters plus 28.1 millimeters. And then we divide that by the number of values there are. Well, we could see that there are 1, 2, 3, 4 values, so we divide by 4. Equals, let me bring up a calculator really quick. And 27.9, plus 28, plus 27.8, plus 28.1. So 111.8 divided by 4 is 27.95 millimeters. Now, just so you all know, I'm going to say this a million times, if you do not include your units, you will not get full points. If you do not show your work, you will not get full points. Make sure you follow your units all the way through. You have to write them the whole time. You can't write them at the beginning and at the end. I want you to follow them the whole way through. And I want you to show your work. Alright? So that's our mean. That's our average. 27.95 millimeters. Alright, then calculate the percent error for each set of measurements. Alright, so we have the formula for percent error up here. It is the absolute value of the difference between the measured value and the accepted value times 100 divided by the accepted value. Oops. So, let's see here. So that's going to be the absolute value of the measured value, 27.95. Remember I said the average is going to be measured value, minus accepted value. Right here we have a gold coin has an accepted diameter 28.054. So minus 28.054 millimeters, close the absolute value, times 100 divided by the accepted value. So divided by 28.054 millimeters. And notice you've got millimeters in the top and millimeters in the bottom. Those are going to cancel, so you're left with just the percent. So if I do that math, 27.95 minus 28.054, absolute value, make that positive, times 100 divided by 28.054, and that gives us 0.37. And because we've already multiplied by 100, that is in percent. So 0.37%. So that is our percent error. Now I'm going to leave it to you to do the same math for student B. And they're going to have which student's data is more accurate. So again, use your definition of accuracy up here to say which student's data is more accurate. And I would also like you to give me a why. So explain why it's more accurate. Here, which student's data is more precise. Also tell me why. And which student has a better percent error. And again, tell me why. And it says better percent error. It doesn't say larger. It doesn't say smaller. It doesn't say more positive. It says which student has a better percent error. So remember what I said earlier about your error, whether you want to have a big error or a small error. Alright? Okay, so moving on. Uncertainty. So here, there is always a degree of uncertainty during measurements. Uncertainty in measurement is due to the precision of the measuring tool and the precision of the person doing the measuring. Right? So, numbers attained from measurements are not exact values. So I could sit there with a ruler and measure, 27.9 millimeters, but if I get a micrometer, I can see even closer, and I can get even more of a fine scale. And if I could go and I could take a magnifying glass and I can look really closely, I can get a microscope and look even more closely and get down to like 28.2459218 millimeters, whatever it is. You can keep going forever, and you're never going to get a perfectly exact value. So, knowing that, we have to consider the fact that we can only go as far as our measuring tool lets us measure. So numbers recorded in a measurement include all the certain numbers plus one uncertain number. These are called significant figures. So here, you can see that this measuring tool only has lines for every centimeter. It doesn't have lines between them. So because of that, I only know that this pencil is longer than 1 centimeter. I have to estimate the next digit. So put an estimation in here. Do you think that looks like 1.5 centimeters? Do you think that's 1.1 centimeter? Do you think it's 1.9 centimeters? Guess how long you think that is based on the where it is relative to the markings. Alright? And so you just type in a single number there. Right? You've already got the 1 point. So put in a single number. Here on this one, you can see that the tip of the pencil is past 1.1 and short of 1.2. So, I know that it's at least 1.1 centimeter. I can estimate the next digit. Again, here we have 1.1, and you estimate what the tip of the pencil is at. Is it 1.15? Is it 1.19? Is it 1.11? That's up to you. So put in a guess, again, just a single digit. At the bottom, At the bottom here, every measured number has one uncertain digit. This will be the last digit written. Circle the uncertain digit in the following measurements. So you take these circles, all 6 of them, and you would drop it over what you think the uncertain digit is in each number. Here's only one number, so I can just go ahead and put it there. Right? And so you decide which one you think is the uncertain digit, and you put the circle there for all 6 circles. Alright. Now down here, measurement type with, I don't know why it says with units. You just use either centimeters or inches, whatever. Either way, I want you to measure the length of these blue bars. Right, so you're going to take a look at the ruler and measure how long you think each blue bar is. Then down here, when reading a graduated cylinder, it is important to read the bottom of the meniscus. The meniscus is that curve at the top of the water. Right, the water is going to look curved. Always read from the bottom of the curve. The same rule applies. You are allowed to write these certain digits and then one guessed or uncertain digit. So in this case, we know that it's more than 43 milliliters, or at least it's at least 43 milliliters. So then you can guess an initial digit. So you say 43 point whatever you think it is. All right. Now down here, once again, you take your measurements. Now these are all right at the lines, honestly, so you just go ahead and tell me the measurement. You don't have to add an extra guessed sig fig, because if I were to look at these and guess, I'd say it's 0.0 for all of them. All right. And then down here, last page. All right, last page. Oops. Numbers in science. Seeing numbers. Picture a football or soccer stadium. How many people do you think the stadium can hold? I'm not going to grade you on that. It's just a guess. Now picture that same number as pencils or lollipops. Can you see how much space it would take up? Probably not, because the human brain doesn't have the capacity to visualize very large or very small numbers. This is true. Even very smart folks have a very hard time really picturing very big or very small numbers. It's one of the reasons why people get so confused about evolution. We have a really hard time imagining time scales outside of human lifespans. So how can we represent these numbers that we use so frequently in science? We do it by using scientific notation. Scientific notation is a way to represent really large and really small numbers. Numbers written like 115 million aren't written in standard notation. Numbers written like 1.15 times 10 to the 8th are written in scientific notation. So those two numbers are the same number. And this is why I gave you some exponent work to do, because this is where we're going to be using exponents. All right? So let's start over here. Let's start here. So a number in the ones place. So this is the format for all scientific notation numbers, right? You're going to have a number in the ones place, then a decimal point, and then as many numbers as necessary after the decimal, times 10 to the something, any positive or negative exponent. Okay, so which of these numbers are correctly written in scientific notation? Well, let's take a look at the first one. It's got a number in the ones place, check. It's got a decimal, check. As many numbers as necessary after the decimal, okay, check, check. It's got a couple numbers after that. Times 10 to the something, 10 to the 4th. All right, that first one is correctly written in scientific notation. It's got a number in the ones place, decimal, as many numbers as necessary after, and then times 10 to the something. Excellent. Your job is to put the second star on the other one that is correctly written. So you will figure that out as part of the assignment. And lastly, down here, your calculator can perform scientific notation for you. To do this, you have to put your calculator into scientific mode. So depending on what calculator you have, because I don't know what model of calculator you have, I can't tell you exactly how to do it, but take a look and see if you can find a button that says like Sci, SCI, or SCI/ENG, which is scientific/engineering. So you can change the mode so that when you type in a number, and hit enter, it will automatically report it as scientific notation. So using your calculator, or you could probably find something online that does it for you either way, or if you really want a challenge, just do it yourself based on that formula. Write each of these numbers in scientific notation. So I'll go ahead and give you one. So here's 80. So 80, let's see here. We need a number in the ones place. So we've got 80 has a number in the tens place, not the ones place. So we're going to say, so we're going to move that over. We're going to say 8, okay, and then a decimal, and then as many numbers as necessary after the decimal. So I'll say 0 because you only have that, you only need that 1. All right, times 10 to the something. So 8 times 10 to the what gives you 80? Well, 8 times 10 is 80. Another way of looking at it is say 8 times 10 moves that decimal over by 1 point. So 10 to the, I think it's Control-Shift plus is a shortcut. Yes. 10 to the first power, right? 10 to the first power is 10. So 8 times 10 to the first is 80. So that is how you write 80 in scientific notation. And you will do the rest of those for your homework. Whoops. So that is my video. So that's my video on how to do this assignment. I hope that it was helpful to you. I will definitely be grading you a little bit more tough if you are doing this assignment after this video has come out, just because you have all the resources to do it. So best of luck to you, and go back there and do that assignment because it's worth a lot of points. See you later.